Alright guys, this is Unit 1, Atomic Structure, Section 1, Atoms and Ions. So over this unit we're going to be covering atoms in general and what is going on inside of them. So throughout this video you're going to see a lot of bolded terms. For each of those bolded terms you need to know the definition of them. And what we found in the past is that most people do well with understanding the topics, but they don't do well with the vocab itself. And if you don't know the vocab, you're not going to get questions right on the test. So I highly recommend getting started right away with just making some flashcards, going through them a little bit every night, just a few minutes, every single day, so that you don't miss any of the vocab. So we've talked about elements already, and remember that elements are anything that is on the periodic table. If it's not on the periodic table, then it's not an element. Sure, there are a few that we haven't found so far, but for the most part, we are just creating new elements in the lab at this point. We are not really finding new elements out in the wild. So just for the definition of what an element is, it's a substance that cannot be broken down into simpler substances by chemical or physical means, meaning it's really hard to break up an atom. It's really hard to break up elements into smaller pieces. It consists of atoms all having the same number of protons, so that's really important. That means that every single carbon atom you find is going to have the same number of protons inside of them. And we'll get to what a proton is exactly in a little bit, but today we're going to be referring to elements either microscopically, as in individual atoms, and also macroscopically because they can clump together and form chunks with hundreds and thousands of atoms of the same atom making up that chunk. Like I can have a hunk of iron with a whole bunch of iron atoms inside of it. If you look on the periodic table, you'll notice that all of the elements are represented by a chemical symbol, and this chemical symbol is either one letter or two, but always that first letter is capitalized and the second letter is never capitalized. If you capitalize the second letter, that's suggesting to me that a new element is present. Not that you're talking about the same one that just has two letters, so be careful. For example, we have iron is a two-letter element, or let's do iron, Fe. First letter capitalized, second letter not. Chlorine is one that trips people up. Capital C, lowercase l, that is chlorine. If I were to do this, that would be carbon and iodine. I know that they look very similar, but this guy is chlorine, this guy is carbon and iodine. One element, two elements. So be careful with your lowercase, uppercase. And most of the time you'll notice that these letters are close to the name in English, but sometimes, like with iron, iron does not have Fe in it, but it comes from the term ferrous, which is, I believe, Latin, possibly Greek, I don't remember. But there's the Greek or Latin terms, or sometimes the German terms, that the element symbol is based off of. So here's some more of those elements. I just want you to do a quick scan, pay attention that some of them look like the element name, some of them do not. And remember, first letter uppercase, second letter not uppercase. So just so you guys know, within the next couple of weeks, we are going to be having element quizzes where you are going to be tested over being able to match the element name to the element symbol. So, like, I would give you iron, and you would have to write down Fe. Not from a word bank or anything, you just need to know that iron is Fe. I would give you Pb, and you would have to know that that is lead. And you'll have to do that for the first 40 elements on the periodic table. And we're going to give you guys, I believe we do it 10 at a time, so you can get started on that if you would like to, but we'll give you a heads up as we get to those quizzes. Usually they're a big grade booster. But you'll need to do 10 at a time. Flashcards are super helpful, and just be aware that that's going to be coming up. The first 40 element names and symbols, and yes, spelling will count. So this is the periodic table. This is like my pride and joy. I love the periodic table. I got periodic table shoes. Don't know if you've ever noticed that, but I wear them all the time. And we are going to be spending so much time getting into this because honestly, this periodic table is genius. The amount of information that you can get out of this is insane, and I just find it incredibly fascinating. Right now, all you guys need to know is there's a bunch of elements on there. Cool. We're good. So we're going to be talking about what is inside the atom. So you guys have all seen a million different versions of the models of the atom. We're going to get into the models of the atom a little bit later in the week, but just know that the pictures that you usually see, like the Jimmy Neutron picture or this one that I have in front of you, these are not actually the most correct version of the model of the atom, but it's a lot easier to understand when you're learning, and it's kind of just like good enough for now. But just know that these are not the most accurate, most advanced models of the atom. We'll talk a little bit about those, but we really don't need to use the most advanced one to discuss most of the things we discussed in this class. That's really kind of a quantum physics thing, so we'll get to that eventually, kind of. So all matter is made up of atoms. Atoms are the basic unit of matter. So think back to bio, where cells were the basic unit of life. Atoms are the basic unit of matter. So crazy town, cells are made up of a butt-ton of atoms. Oh, crazy. So inside the atom, there is a nucleus, just like inside the cell, there's a nucleus. But inside the atom nucleus, we've got a couple of different things that we'll talk about. And surrounding the nucleus, instead of having all of the, the ribosomes and lysosomes and endoplasmic reticulum and all that like we have with the cell, all we have are electrons. That's it. So much simpler than the cell. Only 3 parts. That's all you gotta know. A nucleus and a cloud of electrons. So we got our nucleus. Remember, that's the central part of the atom. And here's the part that you need to know. Inside the nucleus, we have protons. Ooh, we talked about those before. And we have neutrons. Protons and neutrons inside of the nucleus. And then the electron cloud is where the electrons are, and those are outside of the nucleus. So here's an example of an atom. This one is a lithium atom, and inside this lithium atom we have 3 protons in purple, and notice that the 3 protons in purple are inside our nucleus here in the center, and we also have 3 neutrons in green, and then around the outside we have our electrons. So this is showing us the electron cloud. We will do some other examples where instead of using an electron cloud, we'll use something called energy levels. So we can use those kind of interchangeably. Usually I don't ask you to draw them in an electron cloud because what an electron cloud shows you is where the electrons are most likely to be found. They're not really in specific locations, but they're more likely to be found in some places than in others. So in this picture where the darker blue is, that's where the electrons are more likely to be found as they're kind of zooming around. But we also can find them in energy levels. And we'll get to what that means a little bit later. But they're still outside of the nucleus. So here's what I'm talking about with a picture of an atom with energy levels instead of an electron cloud. So this is the same atom. We still have the 3 protons. In this case, they changed it up and made it 4 neutrons, but it doesn't really matter. It's still a lithium atom. But instead of just having a random electron cloud going on, this picture shows us those energy levels. Energy levels. And those are those rings. There's 1 energy level, there's 2. And that's really important for when we're talking about bonding with atoms. Remember, atoms aren't just chilling out. They're actually bonding with other things. And the electrons that are inside an atom, the ones that do the bonding are these guys out here on the outermost energy level. Those are called your valence electrons, and the outermost energy level is called your valence shell. Valence shell. And those are the ones that do the bonding just because they're on the outside. It's easier for them to interact with other things. So here's our 3 subatomic particles. There are 3 subatomic particles. Sub meaning under or in, inside, subatomic, inside the atom. And inside the atom we talked about there being protons and neutrons and electrons. So let's start at the top here with our electrons. So electrons, here's the symbol for that, right there with the E with a little -1 sign. And the reason why it has a -1 sign is because it has a -1 charge. It is a negatively charged particle with a quantity of 1. Electrons have almost no mass. They are barely contributing to the mass of the atom. We measure mass in something called atomic mass units, AMU, and these guys have 1 over 1872 AMU. So that's really almost none, almost no mass. And these guys are located outside the nucleus, and we can consider that being in the electron cloud or in energy levels, depending on what type of model we're talking about. Protons, on the other hand, protons are represented by lowercase p. Protons are positively charged, positive 1. They are 1 AMU, and they are in the nucleus. And then down to neutrons. The neutrons are represented by N. Neutrons are neutral. They have no charge at all, a charge of 0. And notice that they are the same mass as a proton, same mass, and they're also located in the same place. So if I'm going to look at this, the nucleus contains protons and neutrons. What charge do you think the nucleus has? Okay, well, it has neutrons. That doesn't give the nucleus a charge, but it also has protons. So therefore, the nucleus is going to be positively charged in the center of the atom, and the negative part of the atom is the outside of the atom. So like I said, since the protons are in the nucleus and they're combined with the neutrons, which don't provide any charge, the nucleus is considered to be positively charged. The nucleus is made up of our protons and neutrons. Remember, those both had a mass of 1 AMU, while the electrons had barely any mass. So the nucleus is where all the mass of an atom is, which is kind of crazy because atoms themselves are super duper small, but the nucleus is really, 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 really tiny, and all of the mass of the atom is inside that teeny tiny little nucleus. And then it's just a bunch of empty space with some electrons floating around that barely have any mass at all. The other important thing about atoms that you need to know is that atoms are considered to be neutral. But wait, I just told you that atoms have negative parts and positive parts. That's true. But when you add up the negative parts and the positive parts together, they need to cancel each other out so that the atom itself has no charge. So that means that protons, with their positive charge, have to cancel out the electrons with their negative charge. Therefore, the number of protons must equal the number of electrons. So let's kind of take a look at what this means. So if I'm going to do some math here, let's say I have an atom with 2 protons. Okay, that means the atom's nucleus has a +2 charge. Okay, so now I have 2 electrons. That means the electron cloud gives you a -2 charge. Those guys are going to cancel each other out and give the atom a charge of 0. So the protons and electrons have to cancel each other out every single time for an atom. So we're talking about these things, atoms, and I said that atoms of the same element always have the same number of protons. So that means, let's start with hydrogen. So hydrogen always has 1 proton. Always. For it to be a hydrogen atom, it has to have 1 proton. That's really how these elements are defined, by their number of protons. If you change the number of protons, you change the element. If this had 2 protons, it would be helium instead of hydrogen. So I've got hydrogen with 1 proton. But I can have different types of hydrogen. I can have hydrogen with 1 proton and 1 neutron. Or I could have hydrogen with 1 proton and 2 neutrons. These guys are still hydrogens, but they have different amounts of mass. So this guy has a mass of 2, and this guy has a mass of 3. So they're the same element, they have the same number of protons, but the only difference is that they have different masses, and they have different number of neutrons, which are causing the different masses. These guys, because they are different, even though they're the same element, we have to call them something different. These guys are considered to be isotopes. They're just isotopes of each other. They're the same element, different masses. This would be like if you've ever heard of carbon-12 or carbon-14. Carbon-12 has 6 protons, 6 neutrons. Carbon-14 has 6 protons, 8 neutrons. And carbon-14 is the one that you talked about in earth science or bio, where you could carbon date things. You could figure out how old they are. And the difference between that carbon and normal carbon is that they have different masses because they are isotopes. We're going to talk so much about isotopes, so if you're kind of confused about this part, don't worry too much, because we have a whole topic on isotopes. We have a whole section of notes on it. I just kind of wanted to introduce it so that the next couple of slides won't be as confusing. If you didn't know that atoms of the same element can have different masses, something else a little bit further will be kind of confusing for you. Alright, so far I told you that atoms have to be neutral. Atoms have to have their charges cancel out. So the protons had to equal electrons. Well, what happens if that isn't the case? What happens if protons aren't equal to electrons? Well, then we don't call it an atom anymore. We call it an ion. And an ion is just an atom with a charge. And there's 2 different types of ions. There's a cation. Meow. Kitty cat. This is a cat. Okay, and cats have paws, right? Kitty cats have paws. And therefore, since kitty cats have paws, cations are positively charged. Positively charged. Meow. I'm going to do that to you all the time to remind you that they are positively charged. And anions are negatively charged. I don't have anything cute for that. It's just an anion. Sorry. And the way this happens, let's do some math here. Woohoo, math! So exciting. Okay, for a cation. Oh, cool. Do you hear my cat in the background tearing up my couch? Sophie, stop it. Go away. Go. She's being a brat. Alright, so we have the cation. And remember, for a cation, they have to be positive. So that means you need to have more protons than, nope, not neutrons, more protons than electrons. So let's kind of do the math on that. Let's say I have an atom with 3 protons. I don't know why I'm writing in a highlighter right now. All right, 3 protons. And I also have, I need to have more protons, so 2 electrons. So here's why that's the case. Remember, protons are positive, plus 3. Electrons are negative, minus 2. What is 3 minus 2? 1. In this case, a plus 1. So if I have 3 protons and 2 electrons, I'm going to have an ion with a plus 1 charge. Now let's do the other way around. For an anion, for an anion, we have more electrons than protons. So in this case, let's do 5 protons and let's do 7 electrons. So that means I have a plus 5 minus 7. What is 5 minus 7? Oh, it's a negative 2. So that is why if you have more electrons than protons, you get a negative charge, and a negative charge causes it to be called an anion. So remember, these are only for ions. Atoms, these guys have to cancel out. But in the event that they don't cancel out, we just call them ions. So to keep all of this straight, so that we don't get it all mixed up, we have all these fancy schmancy symbols, and this is called an isotopic symbol, because you can use it for an isotope. An isotopic symbol, and this symbol contains 3 pieces of information. Well, 4 if you include the chemical symbol, the Be for beryllium. The first one that I want you to notice here on the left, this guy, is considered to be your mass number. Your mass number is the number of protons plus your neutrons. And then your atomic number is down here, and your atomic number is the number of protons. So I can use this symbol to figure out how many neutrons are in beryllium. So if I have a mass number of 9, what is happening? What is happening? Get out of here. Get out. Okay. If I have a mass number of 9, and that equals protons plus neutrons, then I can do some math. Math is fun. Then 9 is equal, we're going to plug in our protons, 4 plus neutrons. How many neutrons do we have? We have 9 minus 4 is 5 neutrons. So you can use this symbol to help you figure out how many protons, neutrons there are. You can also use it to figure out the number of electrons. So I'm going to do some erasing here just to clear up some space. Get rid of all that guy. Come on, go. Get out here. There you go. So we figured out that we have, in this thing, we have 4 protons, 5 neutrons, and now we can figure out the number of electrons. So it says that this guy has a charge of +2. That means that we have more protons than electrons. So if I'm going to figure this out, I have 4 protons plus however many electrons equals -2, +2, sorry. So that means I need to have 2 fewer electrons than protons. So 4 minus 2 equals +2. Therefore, I have 2 electrons. So using this symbol, I can figure out the protons, the neutrons, and the electrons for an atom, or for an ion, or for an isotope. It's super duper handy. You will need to have to write these, so make sure that you can do that. Alright, so we've got a bunch of different examples of sodium. So let's start with the first one. So if we have sodium, and you might want to just pause this so far, like pause it and see if you can do it. Or watch me do one, and then pause it and try and do the other two. So you shouldn't just be like passively watching this, actually try and think through how to do each of these. So the symbol for sodium is Na. Okay, and it says that a sodium atom has 11 protons. Remember, protons are the atomic number, they're equal to the atomic number, and that goes down the bottom left. So we got 11 protons. Okay, we also have 12 neutrons. So remember, up here is where our mass number goes, and that's where the protons plus the neutrons are. So I'm going to have a mass number of 23. And this is an atom, and I'm not going to put a charge up in the top right corner because atoms don't have a charge. Remember, atoms are neutral. So our final answer is that. Okay, for sodium atom, Na, no charge because it's an atom, has 11 protons, and then we need a mass number up top where we have 11 plus 11 gives us 22. So I'm going to pause for a second, and I want you guys to think about, how are these two related? What would I call these guys? They're the same element. They're both sodium. They both have 11 protons, but they have different masses. What would I call that? That would be isotopes. They are isotopes of each other. Okay, now we have a sodium ion. Ooh, that means we're going to have a charge with 11 protons. And now it's saying we have 11 neutrons. Cool, we already did the math of that on the one right above it. So we have 22 neutrons. But now it says we have 10 electrons. So I have a plus 11. Come on. Minus the 10 electrons, because remember, electrons have a negative charge. So that's going to give us a positive 1 charge. And remember, there is a positive charge here, so we are calling this a cation. My cat is currently also biting me. Sophie, you are not positive. Go away. So this would be the isotopic symbol for sodium ion, or sodium +1, with a mass of 22. Alright, so here's where we're going to learn how to actually read the periodic table. So the isotopic symbol is just for writing. That's not what's on the periodic table, that's just how we would shorthand write on an assignment or a test or anything you see online. This is about what the boxes on the periodic table mean and what all those numbers on there stand for. So we already talked about the atomic number. And remember, the atomic number is the number of protons in the nucleus of an atom. It's always the same for the atoms of that element. So all carbon atoms will always have 6 protons, every single one. And the other cool thing is that, remember, for an atom, protons must equal electrons. So if this is an atom, that can also tell you how many electrons there are. So in a carbon atom, there are 6 protons and 6 electrons. Now this part is something we're going to do in our isotope notes. So I don't want you to worry about how we get this number or any of that jazz, but this bottom number here is called your average atomic mass. And your average atomic mass is based off of isotopes. So remember how isotopes all have different masses? Like there can be carbon with a mass of 12, carbon with a mass of 13, carbon with a mass of 14, and the only difference is the number of neutrons. Well, what we're going to do later is we're going to learn how to average the mass of all of those isotopes, and that's how we get that number there. So I want to point out to you that the mass number that we talked about with the isotopic symbol, the protons plus neutrons, that is not the same thing. The mass number is for an individual atom. We can only use that to talk about individual specific atoms. And this number here, the average atomic mass, is for the average of all carbons that exist. Okay? There are 2 different things, and the mass number is not on the periodic table. So I want you to either look up a periodic table, go on your phone, get one, or just click back a couple of slides a couple minutes ago, and I want you to find chlorine. And chlorine is Cl. It's all the way on the right side of the periodic table. And you're going to use that information on the periodic table to answer these questions. So go ahead and do that, and pause, and then go through and answer these questions. So hopefully you've gone through and you've done that. And you found that chlorine has an atomic number of 17. So remember, this atomic number is representing the number of protons. So we also have our answer for right here. And that is always going to be a whole number. You can't have part of a proton. So all of the atomic number stuff will always be a whole number. And remember that when you have an atom, your protons are equal to your electrons. So that means we also have 17 electrons. Now let's say that we have a chlorine ion, and this chlorine ion has a charge of -1. So we always have 17 protons in chlorine. But we need to figure out how many electrons we have to get us a -1 charge. So 17 plus what negative number will result in a -1 charge? 17 plus 18, remember this guy comes out to just a negative. This is a confusing way to write this. It's really just this. 17 minus 18 gives us a -1 charge, meaning that we have 1 extra electron on the chlorine ion, also called chloride. So the last thing I want you to do for your notes is I actually want you to go through and summarize today's lesson. So just in a few bullet points, take out the most important information. You might want to look at the different parts of the atom, the subatomic particles, the nucleus, the energy levels, the electron cloud. And then I want you to also discuss what makes an ion different from an atom. What is actually going on the inside of the atom to make it different from what is going on the inside of an ion? Just take a few minutes to do that. You shouldn't be writing more than 3, maybe 4 sentences there. So we're going to be doing a ton of practice going through to calculate different numbers of subatomic particles. So I want you to make sure that you are bringing your calculator next class. And again, make sure that you guys are going through and you're making flashcards for all of these vocab terms because they are very commonly misused, and I want you to make sure that you get them right for all of our tests and quizzes.